Okay, so this is our last batch of videos for Math 1410 Linear Algebra. In this first video we're going to look at some of the properties of the eigenvalues and eigenvectors of a matrix. And then from there we're going to move on to talking about diagonalization and some of the applications of diagonalization. So to begin with, we start with a definition and a theorem. Now these are results that you're familiar with if you completed assignment 5. We defined what it means for two matrices to be similar there. We said, well, we would say that B is similar to A if you can find an invertible matrix P, so that I can write B as P inverse times A times P. So that's what it means for these two matrices to be similar. And if I take this equation, if I multiply on the left, if I multiply both sides on the left by P, right, then I get to P times B is equal to A times P. And from there, I could go one step further and I could say, well, you know, I could write A as P, B, P inverse. Or if you like, I could think of this as Q inverse B and then Q, where Q is the inverse of P. I could do it that way, right? Because the inverse of the inverse gives you back the original matrix. And so saying that B is similar to A is the same thing as saying that A is similar to B. Right? So this is a symmetric relation here between these two matrices. In fact, this is an example of what's called an equivalence relation. So not only is it sort of symmetric between the two matrices in the sense that saying A is similar to B is the same thing as saying B is similar to A, every matrix is also similar to itself, because I can take P to be the identity matrix. And similarity is also what's called transitive. If I know that A is similar to B, and I know that B is similar to some other matrix C, then I can conclude that A is similar to C. And what happens, and you study these a little bit, if you take Math 2000 you'll learn a little bit more in detail about equivalence relations, is that any equivalence relation takes your set, in this case the set of all matrices of a given size, and chops it up into what are called equivalence classes, so different subsets where everything within one of those subsets is similar to each other, right? So all the matrices that are similar to a given matrix, they all go in one group, and then if I find some other matrix that isn't similar to the ones I already have, then that starts a new group, and so on until you've exhausted all possible matrices. And the theorem here says that within any one of those groups, within one of these equivalence classes, within the group of all matrices that happen to be similar to each other, every matrix in that set is going to have the same trace and the same determinant, and also the same eigenvalues. Now, the first two, trace and determinant, that was done. You guys did it for me on assignment 5, right? Trace and determinant. These were the third problem on assignment number 5, right? And if you didn't do assignment number 5, well, you can also find these results and the proofs in the textbook. So maybe you should have done assignment 5. All you really had to do was go find the appropriate page in the textbook and copy and hand it in, and you could have got at least part marks. But in any case, perhaps you didn't get around to that portion of the textbook, and if you want to, you can go take a look. You'll find that it is indeed there. Now, what we didn't prove yet, what I didn't assign, because we hadn't talked about eigenvalues yet, is we want to argue that similar matrices also have the same eigenvalues. So how do we prove that two similar matrices have the same eigenvalues? So what we want to do is we want to suppose two things. One, lambda is an eigenvalue of A. And remember what that means. That means that A times X is equal to lambda times X for some non-zero vector X. And the other thing we're going to assume is that B is similar to A, right? So B is equal to P inverse times A times P for some invertible matrix P. Okay, and what do we want to conclude? We want to conclude that this same number lambda is also an eigenvalue of b. Okay, so how do we do this? Well, what we do is we say, you know what, if b is p inverse times a times p, as we noted above, I can write a as p, b, p inverse, and that means that a times x is p, b, p inverse times x, and on the other hand, that's equal to lambda times x, because we're assuming that a times x equals lambda times x. All right, so let's take this equation here, okay, and let's multiply both sides by p inverse, and what do we get? We get, if I multiply on the left by p inverse, then I cancel it from the left hand side of this equation, and I get b times p inverse x is equal to p inverse times lambda x. But lambda is a scalar. I can pull it out of this matrix product and write this as lambda times p inverse times x, right? And so now I can see that lambda is an eigenvalue of b, and I even know what the eigenvector should be for this eigenvalue lambda. My eigenvector should be p inverse times x. Well, there's one thing to be concerned about. How do I know that this is non-zero? Well, I know that it's not zero because P inverse is an invertible matrix, right? And we know that there are no non-trivial solutions to a homogeneous system with an invertible coefficient matrix. So if I take a non-zero vector and I multiply by an invertible matrix, the result has to be non-zero. Okay? And so that tells me that similar matrices have the same eigenvalues. So, why is that useful or interesting? Well, there are a number of situations in which it's easy to determine the eigenvalues, right? One such situation is that of a triangular matrix. Okay, so for either an upper triangular or lower triangular matrix, and in particular for a diagonal matrix, you can immediately determine the eigenvalues by just looking at the numbers on the diagonal. So the diagonal entries on a triangular matrix are the eigenvalues, right? So if you have a matrix which is similar to a triangular matrix, well, you know the eigenvalues for the triangular matrix. Similar matrices have the same eigenvalues. So as soon as I know that my matrix is similar to a triangular matrix, I know the eigenvalues for my original matrix. Okay. So we can see how similarity could be useful here in the context of determining eigenvalues and eigenvectors. Now, by the way, this is not quite as convenient as you might think, because it turns out that in order to kind of determine this triangular matrix, which is similar to the one you started with, the standard procedure for figuring out what that triangular matrix is begins with finding the eigenvalues. So it's sort of a vicious circle. If you had the triangular matrix, you would know the eigenvalues, but in order to get the triangular matrix, you have to figure out the eigenvalues first. So that's, maybe a downside here. But the way to see that this does indeed work, right? If my matrix looks like so, if it's upper triangular, well, let's be suggestive and put lambdas down the diagonal, right? So let's say it's upper triangular, so zeros, 0, right? So everything below the diagonal is a 0. I've got possible non-zero entries above the diagonal. I don't care what they are. I've got some entries. And so when I do x times the identity minus a, right? When I try to set up my characteristic polynomial and take the determinant of this guy, well, you can see what you get. You're going to get x minus lambda 1, x minus lambda 2, and so on down the diagonal. All these other guys are still zeros, and we know that for an upper triangular matrix, right, so this is a difference of two upper triangular matrices, so it's still going to be upper triangular. And we know that you determine the eigenvalues, or you determine, sorry, the determinant of an upper triangular matrix by simply multiplying down the diagonal, right? So the characteristic polynomial, it must be x minus lambda 1 times x minus lambda 2, and so on down to x minus lambda n, right? And so we know that the eigenvalues are simply the zeros of this polynomial, and there you have that polynomial sitting there in front of you already factored, and you can see that the zeros are exactly the diagonal entries. Good. Now, in this note here, I've mentioned that for a diagonal matrix, not only can you immediately read off the eigenvalues, but the standard basis vectors, the ones that have a 1 in one of the positions and zeros everywhere else, those are automatically eigenvectors, right? Well, what about for a triangular matrix? Is that still the case? Not necessarily. Here are three matrices with the same eigenvalues, okay? All three of these matrices have one eigenvalue. So for all three of them, we simply have lambda equals 2 is the only eigenvalue, okay? Now it's repeated 3 times, right? But lambda equals 2 is the only eigenvalue, right? The characteristic polynomial here would look like x minus 2 all cubed, right? So it's a repeated root, if you like. It shows up 3 times. So if I were going to try to find eigenvalues in eigenvectors, well, this is sort of interesting, because if I did, for the first one, if I do a minus 2 times the identity, well, a is 2 times the identity, so I just get the 0 matrix, right? And so when I'm looking for an eigenvector, right, what am I trying to do? I'm trying to find a non-zero vector x that solves this homogeneous system. Well, 0 times x equals 0, that's going to work for any vector x, right? And so any x will do, so every non-zero vector is an eigenvector. And so then I have to think, well, okay, I don't want to write down any, I want to sort of, come up with the basic eigenvectors, right? Think about writing down the basic solutions to the homogeneous system. Well, the basic solutions are just going to be that I could take x equals I could take j, I could take k, right? Because every vector can be written in terms of those 3. So I have sort of 3 basic eigenvectors in that case. Now, when I do b minus 2 times the identity, right, you can see that something survives. That 1 up there sticks around, right? And so if I were to solve, if I were going to do b minus 2 times the identity times x, set that equal to 0. Well, that matrix there is already in reducer echelon form. Notice that this is one of these rare scenarios where there is no leading one in the first column. The first column is entirely 0, right? So for the corresponding homogeneous system, that first row would say 0x plus 1y plus 0z equals 0. So y has to equal 0. That means that a general eigenvector is going to look like this, x, 0, z, right? So x times I plus z times k, right? So the sort of basic solutions are going to be either x equals I or x equals k. But this time there's only 2. We had 3 options for the matrix A. There's only 2 options for the matrix B. And you might guess that for the matrix C, if I do C minus 2 times the identity, right, now I get this guy, right? And this time, if you were to kind of play around and solve the homogeneous system, well, you can see that the first component can be anything because there's no leading one in the x column. But y and z both have to be equal to 0, right? So in this case, every eigenvector is a scalar multiple of a single basic eigenvector, simply I, right? So the basic solution here is only I. So for the matrix C, there was only one eigenvector, one basic eigenvector corresponding to our eigenvalue, right? The matrix B had two. The matrix the matrix A had three, right? And so we'll see that. So you can see that not all matrices with the same eigenvalues are created alike. You do have to pay a little bit of attention to what's going on off the diagonal. Okay, so that's sort of the basics for the properties. In the next video, we're going to look at this process of diagonalizing a matrix.